Hello and nice to meet you to this new episode of Wigbit. In this assembly lesson we would like to make a counter with LEDs on external board. The first thing is that we said we would like to have a new name for this, and I renamed it to LED underline counter. And today we have the date, we have the 21/4. For all my American viewers, this is the April 21 April 22. Okay, and the author is correct. For Windows you need this, and for Linux this, and also we would like to make here a history. What does that mean? We say it on the order that we have here a date 21/4/04. That is we're doing the we're making a LED counter. Okay, that sounds correct. First, what do we need for the LED counter? We leave the blinky on the same board, we said the number LED is here, and we see we need description for that. It's very easy to understand, and we say the first what we need is a counter, a LED counter, and we say this definition and say counter LED. Is that good? Yes. Okay, it's on R20. Here's the counter for LED, and this we move to the next 221, so we have a little bit orientation. We can also say counter 2 to this counter, and this counter will show us what's happened outside. Then we need a counter LED and a counter 2, or for the timing. We need for the timing also a counter. This counter is reserved for the blinky. We need a counter 2 and a counter LED. Counter 2 for the timing and a counter 2 for LED. And define a counter for LED. This is R21. Should we do that so? Yes, we do that so. This is the counter value. Yes. This we move back one step to register 21. So this is counter to time. I think I say time. Time LED is for the LED. Counter for the LED time. So the LED time we must also initialize here, and we say the counter for the LED is, we say equal LED time is, what did we say? We have the 10 milliseconds, all the cycle, we have 10 milliseconds, we take 100 milliseconds, for example, this means 0XOA. This is 10, 100 milliseconds is 10 times, and it's 0x0a. This is the LED counter. LED counter timing. Okay, you see? And now we say also here, this is for sub 2. And this is for sub 1. Why we do that? In case of that, if we would like to interchange something in that we know what for subroutine is need from this, and this is sub 2. This means subroutine. Also, this is also for subroutine 2. Subroutine 2. We should write it. Sub means nothing. Subroutine 2. You can see this. Blinky time. Blinky time is for sub 1. Subroutine 1. Yep. You can see. For sub 2. And then we say abort. We say abort. The port B we can use. You see that? We can use this. And here we have the LED 1. Here we have the LED 2. And so on. LED 3. LED 4. LED 5. LED 6. LED 7. And here you have the LED 8. Is that a good idea? No, it's not good. We have here the 7, the 6, the 5, the 4, the 3, 2, 1, and here we have the 0. Oops, it's the 0. What we're gonna do is we use the port outputs here for these LEDs. We have a counter with 8 bits, and this must be standing all on the direction on out. Here we have all outs. That means here is a out, out, outboard, outboard, out, 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 and out. Okay, all these ports are switched to the out direction, and the init port was here was 0, and we start our counter by initialization with the out. That means we have the counter LED we have inside the register. So, and not only the LED, we have also the equal, we have the LED value init LED value. The start from the count is 0x00. It starts at 0. Start at 0x00 and count till 0xFF. So in binary is that so 0b, this is binary 2 4 5 6 7 8. Okay, this is correct, and we count to this position. This is the highest value. This is in decimal. Very simple. It's 0 in decimal. Or we can also say 0D. Say this is 0 and count till 255. Okay? For all the people they don't understand the binary, hex is a very simple example here. We count the highest bit, the MSB, yeah, it's the bit number 7, yeah. It's bit 7. And the bit 7 is a value from 128. Correct? And 6 is a value from 64. And 5, oops, and 5, 32. Oh, hey, come on, the brackets. 4, 3, 2, 1, 0. Okay, after this no, then brackets, 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 brackets. The first LSB counts the ones. Then these are the 2s, 4, 8, 16, and so on. For example, if you have a number in binary in the counter, it's something like, okay, now 2, 4, 6, 7, 8. Okay, so now it's correct. That means it counts. This is bit number 6. This is 64 plus 32 plus 0, nothing, plus 8 plus nothing plus 2 plus 1 is, how much is this? We need a calculator. It's very easy to understand. 64 plus 32 plus 8 plus 2 plus 1. It's 107. Is that correct? 107. Is that correct? Have here 107. We switch to the informatical. It's 107 and the bit is 0, 1, 1, 0, 1, 0, 1, 1. Okay, you can see that here in this row. Yeah, it's correct. And in hex, it's 6B. This is 0, 6B. Okay. So the counter is running. The counter starts up with the 1, and every time if it's running in the circle, it's 1. It counts then 2, and then 3. Both of these bits will be flashed, and then 4. Only this is 1, 0, 0 in binary, and so on. And we would like to watch that on the LED mask. Now we're gonna do the compare. Here is the port B is the out. We initialization interrupt, okay. And now we init the bus. Oh, did we not know? This is the equation. Start, jump reset vector. We go to the reset vector, and here's the initialization. Load the blinky time and the status and the timer too. And now we are going here and say we would like to init LED timer value load immediate counter what? Counter 2? No. What is the counter? Immediate counter LED we need load counter, look here, counter LED, this is the value. With a value, it's not null, it's init counter or start counter. What did he say to this counter? Init LED value. Init LED value, okay, okay, init LED value. The start value of the LED counter. Load the start of the LED counter. You can see that. Okay. Then we are making the timing. We load counter 2 with the timing was what was the timing? LED time. We say LED 100 milliseconds time. Okay, we say this LED 100 millisecond time. Go back, LED 100 millisecond time. Where we are? Not here. We write here LED 100 milliseconds time. This load the timing 100 milliseconds for the counter, for the LED counter. Also here okay. So we initialize this and we count back. This is a countdown, correct? And now we go to our control and say the follows. We say rcall LED counter. This starts the subroutine 2 and subroutine 1. You can see it's the blinky. First blinky was called and then a LED counter was called. You see? LED counter. We make here a line that you understand. Here is the end of the program. Now we say LED counter double point. We make a label and we say the first what we say is the same as here. We say compare immediate. Oh, sorry. What was this? We say here compare immediate counter 2 with null. We are requesting 100 milliseconds divided by 10 milliseconds is 10 times, and we compare counter 2 with We test it. If this is equal, branch if it is equal, branch if it is equal, then jump to LED counter say update or increment. If the counter 2 is equal 0, then jump to LED counter increment. Okay, that means if not, decrement counter 2. But I think so it's not counter 2, it's have a other name. The counter from a LED is, what is the counter from the LED? Counter LED. Counter 2 time. Counter 2 time. We change it to counter 2. We change it to counter 2 here. I'm sorry. Change it counter 2. And so we don't. This is the timing. Decrement this. And if not, jump to the LED counter end. This means counter 2 minus 1. All the loops decrement it. All the loops decremented. It's running here inside this and decrement the counter 2. And if it's correct, it reloads. It's the same that Blinky does, but at Blinky we do this. And then if nothing to do, then end. Then jump to the end. Okay? Now we're making the end. We say LED counter underline end. Double point, this is a level, and we are making here the return. It goes back, returns where it comes from. Okay, but we have that now. We're going to the LED counter increment double point increment. What is here? What we're gonna do here? We increment the counter, not the counter 2. We increment the counter value. What is the value? We increment this register. We increment the counter LED. Okay. We increment the counter LED. That means counter LED plus 1. Correct? We update it and we do that. We update it, and then what we're gonna do, we copy the value. We copy the value to the board. To which board? We said to the board B. We have here the board B. Look here. Board B. Is that correct? The board B. Was that the port B or not? I don't remember. Port B. Port C is the other for the control and for the LED, and the port B. We update the port B. We say out. We say out. Port B. Counter underline LED. We move the value of the counter underline LED out to the port B. There are no. There are the LEDs connected. Correct? LED is connected via a resistor. We need a resistor too for the. And now we load the timer. The counter 2 will be loaded. We must reload the counter. It's the same like here in the upper program in the blinky. And we say load immediate counter 2 with what? With counter value. So what is written on here? Init LED value. LED 100 milliseconds time. LED 100 milli. LED 100 milliseconds time. We reload the timer. Well, not the timer with the counter. We reload the counter 2 with the time for 100 milliseconds. Okay? We increment the counter, we move the counter out, and we increment it and should we load it? No. After 100 milliseconds, it's running in, it's 0. It's running in, it's 0. We increment the counter increment. We move it out. We load the 100 milliseconds again. And then we are returning. This is finished now. Now I come back to the assembly and there was a failure inside, and the first failure what it is the board initialization. Here we go. We have here B, C and D, and now we have here C. That should be D, delta. Yep. This is the first what we change. And then there was an increment problem. Jump to the increment, not blinky. Here it is. LED counter increment. Look, here is the failure. LDE, LED count increment, and there was also other failure too. We started now. Okay. Was a failure too. Just a moment. So we are now here at the assembly tool, and if you have a watch here, let me know. We change to the AVRA and set ATM328 LED assembly, and we would like to have a list file. It's called like also ATM LED, but list. We start it, and we can see 76 words are translated, and we said ATM and list LED LST. Now we have the counter here, and we go back. We have here the list of the timer and whatever, and the program. We see here the the program. You see here the reset vector, and interest-wise here you can see the code, what is generated on the address. And you see now on 100 here is a E0 and 08 and so on, and 102. But why is that so? The organization is in 16-bit. Address have 2 bytes in this controller. The flash is organized in 2 bytes from the start to the end. Look here, start, it's 2 bytes. 2 bytes, all the time organized in 2 bytes. The whole program. On the kitchen table, we doing the assembly again, and we have here, for example, we have here a board. Yeah, this is a board pin. I hope so you can see this. And this board pin out, we are installing a resistor and a LED in direction to the ground. The ground is here written, and this 0 volts, and this is the LED. I'm sorry, I must doing this. This is the LED, and this is the resistor. It's R1, okay? And this resistor limiting the current, and it's very easy to understand. Here we have 3 volt 3, this is 3,3 volts, and we would like to have here a current E with, what is 1 milliampere. 1 milliampere. The red diodes are having the breakthrough voltage from the volts we can measure. It's very easy to understand, and we have here a measurement instrument, and we do that now with the diode tester. If you have your own, this is with 3 volts. Yeah, you can see here 3 volts. 3 volts. Here we have 3 volts, you see that? And we take a LED from the LED thingy here, and we measure it. Is that correct direction? We must measure the correct direction. No, it's the wrong direction. The long pin is the plus and the other is the minus, and you see 109. It's 1.8 volts. Yeah, the LED flashing 1.8 volts. Hope so the logo is not in the way. You see, 179. Okay, we say 1.8 volts are the needed voltage. That means the drop here, from this point to this point, is 1.8 volts at 1 milliampere. You see? And the drop from here, 3.3 to here, U drop, or delta U, is 3.3 minus 1.8. Oh, it's complicated. It's minus 2. It's 1.3, 1.5, 5, 6, 7, 8. Yes, it's 1.5. 1.5 volts is the drop here. I hope so this is correct. I'm too stupid to calculate now. It's crazy. I cannot. 1.8. It's 3.3. Yeah, it's correct. It's 1.8. I must use the calculator in the background. Shame on me. Yes. And 1.5 volts divided, the number is so, we have the resistor. The resistor is very easy. The R1 is U, delta U, divided by the current. It's 1 milliampere. And this means is 1.5 volts divided by 0.001 ampere. It's 150 or what, huh? It's 1.5. 1.5 divided by 0.001, it's 1 milliampere, it's 1500 ohms. It's 1500 ohm. You can see 1500 ohms. Or should we bend it here? It's also possible. We bend it here? No. I must think about putting the diode here. We must have a row of these diodes, yeah? And be here, okay? Super. And we take a second diode, put it here. Okay, and now we sort this up. And making also again a resistor. Insert it here and here. Resistor again. You see? The resistor again. And so on. I hope so that the program is running. We say the yellow is here. Here is the 0, the first bit, and so on. So we have the 8 in a row, 2, 4, 6, 8, and now the yellow is the bit number 0. We must insert it here. Then we have the orange is the bit number 1. Have it here. Then the red one is the bit number 2. We have it here. We have this here. No, wrong hole. And this is the number, and so on. And here we have this number, and this is the bit 7. Oh, it's wrong. It's in the wrong position. The gray is first, and then comes this bit. Okay, so the port B is now here to here connected. And we would like to build in the program. We must connect it to the program and load the program. What I'm gonna do now here is I load the program into the computer, this LED counter hex. And now I would like to connect, the cable is short. I would like to connect it here. And now I would like to shoot in the program. What's happened now? The counter is running. Well, look. What do we have a problem? Houston, we have a problem. Come on, focus. We have here a grounding problem. Look here. I hold it with my finger. Yeah. You see? It counts up the bits. This is the assembly program. What you are writing? It counts up the bits, endless, and starts again. You must know this is the 100 milliseconds blinky, and the second is the half, and the third is the half of the half, and so on. You can see? If I lost my finger, then the connection is gone. Oh no, it holds. Is that not super? This is a binary counter that we built now with the assembly. And you see, it's independent. This running of this blinky blinky have other timing than this have the timing. So you understand why we're making this in sub-programs and programming all out of a timer. This is very important that you must understand this. We have independent programs running on one controller with one task. It's only one task that is running. That was the LED counter for the assembly number 3 in the subroutine 2. I hope so you can also follow this. If you have a computer, a laptop or other computer, you can program this by your own and can build it up. It's easy. Maybe we're doing a user interface now at the next time that we can make a counter with a number, not only with a binary. This is also interesting, and a LCD display will become also a button and a rotary switch where we can make a user interface. If you like my channel, please subscribe, and I say thank you for watching.